Hello, everyone. Our today's guest is Sam Kuypers. You can find his socials on the episode description. Sam, thank you so much for joining me. I want to explore quantum information, epistemology, and the Conjecture Institute. My first question to you is quantum mechanics forces us to abandon classical intuitions about reality, yet it remains a deeply misunderstood field even among physicists. If quantum information is more fundamental than space and time, as some theories suggest, does this imply that reality itself is computational at its core? And if so, what does that mean for concepts like consciousness and free will?
Great. Yeah. So thanks so much for having me. It's a great pleasure to be here. And let's dive straight into it. So I think to answer your last question first, I think the universe at base is not computational, and the reason for that is I don't think that's explanatory. So quantum information is a very foundational field. It's a fundamental field in physics.
Yeah.
But the reason it makes sense of the world is not because the world itself is some kind of computer, which I think that would make all of our physical theories make less sense, because then, what's this computer like? Why are the laws of physics the way they are on this computer, given that they could be anything? Well, are we in a base? And you get into things like the simulation hypothesis. Is there a base universe where everything is being simulated? Like, why is the universe this computer? I think what's, as Deutsch at some point said, what's fascinating about the world is that inside the universe, you can have devices which can simulate other things, that you can have universal computers. The thing that's interesting is that inside the universe, you can build universal computers. That the laws of physics are such that this is possible is not at all obvious and not at all intuitive, but very important both for physics and science in general, because part of what science is building better explanations of the world, which is linked with our ability to simulate other physical systems ever more accurately. So that's so I think at the base level, the world is not a computer or anything like that, but nonetheless, the theory of computation and the theory of quantum information in particular is very, very deep. And quantum theory is an important part of that. So as you also mentioned, we have a theory of physics, quantum mechanics, which is deeply misunderstood, in my opinion, particularly among physicists, but I suppose also the wider public. Sometimes I sometimes see these videos of people saying, recently there was a video that went viral again, where a lecturer said, well, something like, you don't understand quantum mechanics, but after I give this lecture, you'll really not understand it. At the moment, you don't know anything about it, and after I'm done with this lecture about quantum mechanics, you won't understand it at all. Something like that, which is kind of a weird state of affairs to be in, because physical theories are supposed to make sense of the world. We're supposed to go to a lecture and then think, yes, now I understand something more about how the universe works.
Why do you think it's so misunderstood and there are so big misconceptions about it?
I'm unsure. I think part of the answer is that, so I'm of the opinion that the Everettian quantum theory, which is, I would say, quantum theory in its purest form, makes sense of all the difficulties that people have with quantum mechanics. And I suppose, therefore, that the reason people are confused is that explanation, that theory has not gone mainstream, or is not the widely accepted one. And people are, they have other ideas about what quantum theory is. And I think basically none of them They range from making no sense at all to just being insufficient.
Yeah.
And like, for example, the mainstream view of quantum theory is something like we have the Schrodinger equation, things evolve according to the Schrodinger equation. That's all well and good. That's how you do like 99% of physics. And then you add this rule that says when you measure a system, it collapses into a particular state.
Mm.
So it can be in a superposition. You measure it, it's only in one state. And like at that very point, I think everyone should be mystified because there's a sleight of hand where no one tells you what that is. If you were to, ask, okay, well, you've just introduced a new term into the axioms of your theory, and that
Yeah.
term is measurement. Well, I think it's a fair question to ask, what is that? You can't just leave a word undefined and then expect people to think that makes sense. Like, what measurement is supposed to be an actual thing. What makes the measurement happen? And that, I think people just interpret that as, oh, well, we have some kind of common sense theory of what measurement is, but that's nothing fundamental. Quantum physics should provide an answer to what this otherwise undefined term is in order for it to make sense. And that's one of the things that the Everett theory, the Everettian quantum theory does for you. You don't have to assume that there are undefined terms in your explanation of how the world works, which is fundamentally, I would say, unsatisfying. You can't have a theory like that.
Yeah.
Like you could change the word, you could make it something completely nonsensical, and it would highlight just how absurdist it would be. Like, oh yes, after a loop happens, then the system collapses into a particular state, and you go, okay, but you've just said something that is incoherent. Like, we need an explanation of what that word is that you use, and like what are the theories of this thing? And yeah, that's a very strange place to get stuck in.
Yeah. Yeah. Time is often treated as an unshakable foundation of reality, yet quantum mechanics and relativity suggests it might be emergent rather than fundamental. If time is merely an artifact of our particular perspective, what does that imply about causality and our ability to make predictions about the future?
Yes. So I think what you're alluding to is that, for example, in general relativity says there is such a thing as space-time. There's space-time and there's the matter inside it, the matter and energy inside it.
Yeah.
And the whole of space-time is completely stationary because everything that evolves in time, and time is already inside space-time. It's the block universe, as people sometimes call it. And the similar things are true in quantum theory. So you can have similar constructions in quantum theory where the world as a whole is stationary, and it's like particular slices of the world where you get back, for example, particular moments, but all of time is already inside that stationary block.
Yeah.
So time exists in the sense that you can retrieve it by slicing the otherwise stationary thing into pieces, so to speak. I mean, you don't actually physically slice it, of course, but you can imagine looking at a particular moment inside the block. And I think that it actually makes far more sense of what time and change mean in physics than other theories. As I wrote in a recent paper, one of the things that typical theories of time don't really do is they don't explain change, because what you're saying is the world is changing relative to some time parameter, like there's some kind of idea of a clock ticking away in the universe. But if you want to say, okay, well, so why are things changing? And you say, well, it's because time is changing. Then the follow-up question is, why is time changing? Like, why is time itself changing? And how is that anything else but a circular explanation of why change is occurring? And the thing that the block universe allows you to say is, well, I can explain time and change in terms of things which don't change, which therefore is not circular. So the block universe is stationary and is therefore timeless. There's no evolution. The block doesn't change at all. But you can recover time as these slices of the block universe, and therefore you can explain change and time in terms of things which are unchanging, resolving the circular explanation. So this is this is a satisfactory explanation of what time is. And now I've forgotten the other part of your question. So if time is only, what do you say again?
Yeah, yeah. If time is merely an artifact of our particular perspective, what does that imply about causality and how we make predictions about the future?
Yes. So I think I would still say that time exists in the sense that you can recover it. Like, it's a fundamental feature of the block universe that you can recover time from it. And I think our theories of causality are unaffected by it largely, because, for example, one of the things that people worry about, even in like conventional physics, even to constructions that are not the block universe, people worry about their ability to influence the future. Is the future open? Stuff like that. Is how does causality work given conventional theories of physics, given Newtonian mechanics or quantum theory or something? And the reason to worry about it, or the problem that seems to arise, is that for example, Newton's equations are time symmetric. So if you have a solution to some of these equations, then I'm kind of losing my train of thought.
Sam?
Yes. Yeah, sorry. Sorry, this happens sometimes. I kind of lost my own train of thought as I was saying stuff. Let me take the answer from I remember your question, and I'll just I'll just attempt to answer it again.
Okay.
So yeah, I think causality is still preserved within these constructions. Like, I think there is just a general problem of trying to get causality from things like equations of motion, because the equations of motion do not distinguish between the past and the future, basically. Like, the equations of motion generally are time symmetric, meaning that if you do something, then if you have a solution to the equations where things move one way, things move forward, then there's another solution where things are moving backwards. If you also, similarly, if you're given like the initial conditions of the universe, then you can calculate what happens from then onwards. But you can also give someone the conditions of the universe right now, and you can calculate what happens into the infinite future and also what happens in the infinite past. So the equations of motion, they have a hard time capturing our sense of causality. Like, we think causality happens where I do something in the present and it affects something in the future, and it's a one-way thing. There's an error of time, as people say, and that's hard to reconcile with these time symmetric equations. So even without the block universe, there's already this kind of problem of how to make sense of causality in the universe, given that our equations of motion seem to be true. And so the block universe doesn't actually add anything to that makes it more problematic, I think. It is as problematic as current theories are, because the thing that the block universe does is typically it just gives you exactly the equations of motion that we already think are true. So that's kind of what's nice about them. You put in very simplistic assumptions, and then somehow they manage to reproduce the equations of motion which we already think are true. And so everything that's problematic about those equations, or at least the problems that are inherited by them, they carry over into the block universe theory. But so I think that is a thing to be solved, but it's not not something that I worry terribly about either. It's like I think that we will have a satisfactory explanation of causality that captures our kind of intuitive sense of causality and manages to combine it with these kind of fundamental equations at some point.
Yeah.
I don't know how to do that at the moment, but I expect that to be possible. And then if it's solved for conventional theories of physics, it will also be solved for things like the block universe.
Yeah, that's great. Yeah, many interpretations of quantum mechanics attempt to preserve classical realism in some way, yet they all introduce new paradox. If we take the idea seriously that reality is not made up of things in the classical sense, but rather of relationships and information, how does that change the way we should think about existence itself?
Well, so classical realism, I'm not sure what people mean with classical realism. I suppose it's something like so I would say realism in general is just the idea that there is a real world out there and
Yeah.
it exists independently of us and can be understood independently of any subject. And I think that completely carries over into quantum theory. So the thing that the Everett interpretation allows you to do is to have a completely realist theory of quantum mechanics. You just have to assume that there's stuff that we don't see in our everyday lives. Like we are only seeing a slither of the real world according to Everettian quantum theory. In Everettian quantum theory, there's other versions of you, me, of everything around us
Yeah.
that are existing in another universe. In fact, there's many such other universes existing simultaneously, and that's completely compatible with realism. It's just unintuitive. So it's not intuitive to think that there could be other universes out there with copies of us and everything around us in it.
Yeah.
But it definitely is a realist theory because that it just is a real universe. It's a real multiverse, as we tend to call it, which can be understood. It's not subject dependent. It's an objective physical thing, and it gets rid of the major problems with quantum theory that seem to make it not a realist theory. Like, for example, that the state of the observable world seems to depend on whether you measure it or not, stuff like that.
Yeah. And do you think there's like it's possible to see a sober or cleaner reality? Do you think that there's like layers of reality?
I'm not sure what layers of reality means in this context. But do you mean like do you think that it makes more sense of physical reality than classical stuff, than classical theory does?
Yeah.
Because I definitely think that like that there's many. I think the Everettian quantum theory is extremely explanatory. Like it makes sense of things that it was never supposed to make sense of. A favorite example of a mathematician friend of mine, Paul Robichaud, he points out that, for example, we have theories of probabilities. Probabilities are a thing we use often. And if you look at how probabilities are supposed to work, they don't actually make sense in a universe that's classical. Like if you have a single classical universe, it's really hard to make sense of probabilities. I don't think we really can, other than by accepting that there is something like a many universes theory. So I think the only way I could make sense of probabilities is through saying the probabilities are about events that happen in alternative histories, because that seems to be the way that, at least mathematically, probability theory is set up. Like, probability theory never assumes any particular event must happen over any other one, and that's quite jarring if you are used to Newtonian physics, where there is a particle only ever does one thing and definitely doesn't do anything but that one thing. And so how do you combine these two weird facts about the world? That on the one hand, probability seems so descriptive, and yet on the other hand, they can't exist in a classical universe. And quantum theory helps us solve that. The effort interpretation helps us solve that, because there isn't just one thing that happens. There's many things that happen simultaneously, but in different universes.
Yeah, indeed. Yeah, I have one last question about quantum information.
Cool.
The concept of quantum entanglement suggests an instantaneous connection between distant particles, violating our everyday notion of locality. If information can be correlated across vast distance without a direct signal, do you think this hints at an underlying structure to reality that we haven't yet uncovered?
Well, in a way, yes. Well, I think we have uncovered it. So, there's a discussion going on in physics where people worry about exactly the thing you just said, which is how when two particles or two systems are entangled with one another, changing one of them also seems to simultaneously change the other system. Although it only changes in a way that's not perceptible, but it does actually change. So there is an actual change in another system.
Yeah.
And or at least if you look at the mathematics, that's what it seems to tell you. And again, in the Everettian quantum theory, that actually doesn't happen. So you can see in Everettian quantum theory that by writing things in what we call the Heisenberg picture, although that's, I think, too technical, you can see that even when systems are entangled with one another, they do not affect one another, even when they are very far apart. And perhaps a good way to think about that is to think that, let's assume, you and I, we both have a particle, so we both have a qubit or something like that. And if I measure, and the thing that people are puzzled about is that if the qubit is in some kind of superposition, it could be in state 0, it could be in state 1, and if I measure it, I will, with some probability, get the state 0 or the state 1. But what is interesting is that if I get state 0 and our two qubits are entangled in a certain way, then I will know that I will see a version of you who also sees state 0, even though you will also probabilistically observe either 0 or 1. So that scares people. That, like, if I've seen a 0, then I know that if I meet up with you, you also see a 0, even though both events should be probabilistic. And same with if I see a 1, I can see a 1. Again, maybe it's 50-50, so with 50% chance I see a 0, and with 50% chance I see a 1. I see a 1, and then I know, if I've seen a 1, that you will also see a 1. And if you assume that the world branches, so what's really going on is, if I observe the qubit, then one version of me sees a 0, and the other version of me sees a 1. And likewise, when you observe your qubit, one version of you sees a 0, and the other version of you sees a 1. Then one way of explaining this without assuming anything is like affecting the other person at a distance without any mediation of anything is to say, well, maybe what if when I see a 0, then the version of you who sees the one is just invisible to me. So it's not that the correlations occur because there is something spooky going on at a distance. It's just certain versions of you are invisible to certain versions of me, which that is completely local. I can give a local account of that. I can just say, these guys cannot interact, and these other guys can interact, and put that into the interactions for the system. And so these are kind of, I'm sketching
Yeah.
these are the laws of this universe I'm concocting. But this is basically how quantum theory works. And then you can see if I try and meet up with you, then the only possible version of you that I could see is the version of you that saw a 1 if I saw 1. And if I saw 0, the only possible version of you that I could see is the version of you that saw 0. So even if I were to meet up with the version of you that saw a 1, we would just pass through each other. There would be no interaction. We could not see each other at all. And that would explain the fact that there seems to be this spooky action at a distance, as Einstein called it, while still preserving everything that we care about with locality. So this is a completely local theory. There's nothing scary going on. The correlations are really there, but they're just established through rules about which versions of each of us can see each other.
Yeah, that's powerful. Now I wanted to talk about epistemology and the expansion of knowledge. You've written about the intersection of epistemology and creativity, emphasizing that knowledge is not passively absorbed by actively created. If all knowledge begins as a conjecture rather than an observation, what implications does that have for science, education, and even AI development?
So I agree that so education theory at the moment seems very rudimentary to me. I think not many very deep theories going into education. As I said, it's basically people assume that children are passive receptacles of knowledge, so that if you give a lecture, then the knowledge has to pour into their heads. And if they're not, the only things that could stop that from happening are the children resisting the knowledge being poured into their heads, so they're not paying enough attention to the lecture. But if they were to pay attention, then the knowledge would inevitably seep in. It's something like that. So you can see how that sets up people for conflict, because it means that there is an authority who he has the knowledge, and therefore, because knowledge can be handed down in this mechanical way, it's his responsibility to do that, to hand down, to force people to receive the knowledge, and all kinds of nasty things are now legitimized. Like, if students receive knowledge mechanically, well, then their resisting is a bad thing, because if they just stopped resisting, they would have the knowledge, and the knowledge is clearly important, etc. And I think that knowledge is not gotten mechanically. It always has to be conjectured, as you stated. It always requires creative thought, even to understand knowledge that's already known. Because for each person learning a new idea, it's like discovering it for the first time. Each person who learns of a theory in physics or of anything, chemistry, biology, music theory, art, they always have to rediscover for themselves this knowledge that might already have been known for other people, but for them it's very much like the creative process, and therefore blocking people, like hindering them in pursuing the things that interest them, becomes bad, because people have ideas already, people have problems already, people have things that interest them and that they would like to pursue. And because knowledge isn't gotten in this mechanical way, and it's the only way that we can really learn properly, getting in the way of them doing that is a really harmful thing.
Yeah.
So that's my main gripe. I could expand more on the things I don't like about
Yeah.
modern education, but that, like, the philosophical underpinnings, this is one of the main problems, I would say.
Yeah.
And so epistemology, Popperian epistemology, could hugely improve education theory, as well as, I mean education not just in the sense of schooling. I mean education as the process of learning more generally, whether you're in school or outside of school. I think
Yeah.
it could enhance. So it clearly enhances our understanding of learning, because it is the only possible, like, the Popperian scheme for learning, which is you have a problem and you would like to search. You want to know the answer to your problem, and the only way to get it is by guessing and then criticizing your guesses. That is how science works. But it's how all genuine learning works. And if given that that's the case, that should be our basis for a theory of education. Like, if that is how learning anything works, then that means that education should assume that children learn that way. Education theory should assume that. And at the moment it doesn't, and then you get these bad problems like I mentioned before.
Yeah. Yeah, but if learning is fundamentally about conjecture and error correction rather than what we are all taught in our schools, what would a radically better education system look like in practice?
Yeah, so I think there's many different solutions that are possible to that. And the main thing that I always strive to convey to people is that the important thing is that it's voluntary. Children want to learn certain things, and everyone is different. Everyone has different problems, and we should allow people to explore those problems in the way that best suits them. Some people want to watch lectures, but some people want to physically attend lectures. Some people want to discuss with people their own age. Some people want to discuss with people who are older, like with teachers and parents and things like that. And I don't have a one size fits all model, and I don't think there can be such a thing. I think that there can't be a way of organizing education for everyone that suits everyone's needs, except for saying we should try to meet people's needs as best as we can in all kinds of different ways, and allow them to figure out what works best for them, by giving them the freedom to do that without coercing them into one particular option. That being said, the thing I recently wrote a blog about this, stating that
Cool.
we now have technologies that make all of this a lot easier. Like ChatGPT is like a tutor that you carry in your pocket. Like, it can answer any question that you have.
Yeah.
Sorry. Yeah, go ahead.
Yeah, but do you think when we're in school, the system, the people that control the education system really want us to be smart and critical about what we learn?
I think people in school, they have meant that there are many different kinds of people who become teachers, and I think they all have different ideas about what it means to think critically. People who genuinely, so they're one of my favorite authors, John Holt. He used to be a teacher. This is like he's from the 20th century, and he was a teacher. Was very, I guess you could say, idealistic about it. He was hoping, I think, to teach young children about the world so as to prevent another war. He thought, I think, that by properly educating people, by giving them a true education, we could ensure lasting world peace and things like that. So he was idealistic that way. and he ended up writing a book called How Children Fail, in which he observed all the different ways in which the thing that he really wanted, which is to give people a proper education, were not possible because of the ways that schools were set up. So he had to, on the one hand, he was hoping to, enrich people's lives and to give them knowledge that would empower them for the rest of their lives. And on the other hand, he had to thwart them, and he had to do things to them that were horrible, like punishing children, like, scolding at them, things like that. I'm not sure actually he scolded at people specifically, but he observed the ways in which this would happen. He observed the ways in which children would, instead of actually learn things, they would try to appease the teachers, try to appease the parents, and that eventually led him to a thing which he invented called unschooling, which is an approach where you just let children pursue their own interests. And so, there's people like him, there's people like John Holt in the education system who really want to do a good thing, and they just can't. Like, it's the way that it is all set up does not allow them to do the thing that they want to do, and it's a good thing, right? They want to do something that is genuinely positive, but they can't with the way the world works. They can't with the current education system. And then it's hard. It's people are very different from one another, and there's all kinds of people who, as I said, become teachers, but some of them are like John Holt, I imagine.
Yeah, that's right. Now I wanted to talk a little bit about the Conjecture Institute. Yeah, maybe you can start by telling me what are you guys trying to do, and what are your motivation?
So I'm a fellow at the Institute, and I think it's a place for people with sorry, I'm kind of drawing another blank a bit. Do you mind if I briefly go fill up my water, and then I'll try to answer your question? I have this every now and then. Sorry, this is a common podcast experience of every now and then drawing a blank. Yes. I'm not sure what I can say because I'm a fellow at the Institute.
Yeah.
I guess. But I don't organize things specifically. Yeah, okay. Hang on. Sorry. Yes. Yeah, okay. Yeah, okay. Okay. I have a thing I think I can say. So, yeah, I guess we'll take it from here. I know your question, and I can attempt to answer it again. The Institute is a place where people who are interested in some of the ideas that we talked about right now, like epistemology, preparing epistemology specifically, in critical rationalism, in physics, fundamental physics, try to actually solve these problems. And I'm a fellow at the Institute together with other people with similar interests. And I hope the Institute grows. It is, that's also not so good. I'm not a good salesman.
No, it's great. So, yeah, I guess you are all barbarians and Deutschens.
Yes. Yeah, I think we're trying. So, the goal of the Institute is to get these ideas, which are, as we keep stressing throughout the podcast, neglected. Everything quantum theory is somewhat neglected. I think also preparing epistemology is somewhat neglected, or has been in recent years, and to revive them and to see how they are very powerful ideas about the world that can solve a lot of problems. So Conjecture Institute has recently published a book on education theory called The
Cool,
Sovereign
cool.
Child, which I enjoyed a lot. I wrote a review for that recently for the Taking Children Seriously website, and highly recommend it. And yeah, it's about trying to solve important problems using these theories that we spoke about that are incredibly powerful but too often neglected.
Yeah, yeah. You were talking about critical rationalism. Yeah, what do you think is preventing critical rationalism from being more widely adopted? And yeah, how do you see its influence growing in the coming years?
It's a good question. I don't actually. So with all these theories, I don't know why they are not the majority view. With physics, I have some theories with physics for why the Everettian quantum theory is not as popular as it is. But even there, I don't really have I couldn't really explain why that is the case. And the same is true of Popper. I don't know why Popperian epistemology, or what's sometimes called critical rationalism, is not more widely adopted. But the only thing I know, and I guess the only thing that's really important, is that the theories are true, and therefore they can solve lots of problems. And therefore, if anyone wants to make progress on anything sufficiently deep, they will at some point need these theories. So if you want to make progress, at some point there's going to be a point in physics where if you want to make progress on important questions, you need Everettian quantum theory. If you want to make important progress in other areas, you need Popperian epistemology, stuff like that. So although I don't know why the theories are not more widely considered important or true, I think that eventually people will need them. Like there is as I said, if you want to solve deep problems, these theories are going to be important to you at some point. At some point you do need them because they're true.
Yeah, yeah, I get this one idea that one of the Conjecture Institute's core missions is to explore how human potential can be fully realized through better epistemology and institutions. What are some of the most exciting projects or initiatives the Institute is working on right now? And what impact do you hope they will have on the future?
I'm not actually sure. I, I don't know. I'm not on the board, but I I can tell you what I'm working on, and uh, so I'm a fellow at the institute, and I'm trying to advance these theories in physics that we talked about, the Everettian quantum theory, the view that the world is local as well. Those are all things which I'm working on, and I think other people. Sorry, I I don't know. I don't have. I don't feel like I have very good answers to these
Yeah,
questions.
great. Yeah.
But yeah, at least for the aspects on physics, like I think the people working there, myself, and also people like Maria Villaris, who is also a fellow. Our common goal is to expand and popularize Everettian quantum theory and these other related ideas about locality and information processing, in the hopes that we can use it to solve more problems. If the theory is true, we can use it to solve more problems than the other theories can. So that is our aim.
Yeah. 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 In many ways, progress in science and society is limited not by a lack of intelligence, but by bad epistemology. What are some of the most dangerous epistemological mistakes being today? And yeah, what are the Conjecture institutes studying to try to correct them?
Well, so one mistake is this authoritarian view of education,
Mm,
which I mentioned in regards to schooling and the bucket theory of mind, which is the theory that you can pour knowledge into people mechanically, that knowledge is received mechanically, and one way in which they're pushing back against this idea is, as I said, through the book, the Sovereign Child, which I highly recommend.
yeah.
It's a great book showing that the authoritarian, both authoritarian education, but more specifically authoritarian parenting or coercive parenting, are not necessary, precisely because Popperian epistemology says it's not rational. That's one of the conclusions of the theory, is if people have their own interests and they learn by pursuing them, by pursuing the genuine problems that they have, then trying to thwart people to do the thing that you want them to do is not rational. That's arbitrarily preferring some ideas over other ideas, and that's very nicely portrayed in the book. It's a nice read, as I keep saying. It's nice to see how. The author of the book is Aaron, and Aaron portrays his own family in the book, stating how he's managed to resolve many problems with his children in a way that's not coercive, and how they're better off for it. And it's quite inspiring. And it's
That's
promising
great.
to see, that such a book could be published. It's great.
Yeah, I loved it. I already read it, and what a fascinating reading.
Cool.
Sam, thank you so much for joining me. It was a pleasure. I appreciate a lot your time and energy, and see you soon. Thank you so much again.
Yeah, thank you. It was great. It was great being on. Thanks.
Thank you.